Hello students, myself Pallavi Jaiswal. Here in this video, we will discuss the topic of realization of digital linear system. This is part 3. Already I have uploaded part 1 and part 2 in my YouTube channel related to this particular topic only, realization of digital linear system. Here in this video, we will discuss following topic. First one is basic structure for FIR system. And second one is direct form realization of FIR system. Third one, transposed form of FIR network. Fourth one, cascade form structure of a FIR system. Last one, realization of linear phase FIR system. One by one, we will discuss all the topic. First, basic structure for FIR system. In my previous video, I have already told about what is system, what is IR system and what is FIR system. As we know that we have two digital systems. First one is IIR and second one is FIR. IIR system realization technique I have discussed in part 2 video of this particular realization of digital linear system topic. Here in this FIR system, what is FIR system? FIR system is a system whose impulse response are finite in number. That means, for example, here we have one of the system in which we have some length of the sequence is limited to 4. So here what we will understand from this particular figure, that means the length of the sequence is limited to 4. That means length of the sequence is limited to the value 4. That means the system whose impulse response are finite, then that particular system is known as FIR system. This is one of the example. Now this is particular expression, as we know that FIR system is the open loop system and its transfer function expression consists of only numerator term. So here we consider one of the FIR system function, h of z equals to summation n equals to 0 to m h of n z ka power minus n. This particular expression represents that the transfer function of a FIR system consists of only numerator term, hence it has only zeros in their particular expression. So as you can see, the limit is given n equals to 0 to m. What it denote? Particular m denote the length of the sequence for the FIR system. So here there are many realization methods for FIR system available. First one is direct form, second one is transposed form, and third one is cascade form. One by one we will discuss all the topics. And direct form is also known as tap, delay, line structure and transversal filter structure. Now moving direct form realization of FIR system. As previously we will discuss IIR realization technique, in which we have two direct form structure, direct form 1 and direct form 2. So here in case of FIR system we have only direct form realization, in which this is similar to the direct form realization, because in direct form realization first of all we have to realize zeros and then pole. So here as we know that in FIR system we have only zeros term. So direct form 1 is somewhat similar to the direct form realization of FIR system. So here first of all we consider our causal FIR system. Causal system is those system whose values depends upon present input as well as the past input. That means if the value start from 0 till the positive value, so this particular system is causal system. This value must be present from 0 to the positive value of time. So this particular system is nothing but a causal system. So here we consider one equation. As you can see, this is one of the difference equation, and y of n equals to summation k equals to 0 to m minus 1 bk x of n minus k. This is particular one of the difference equation for FIR system. As you know that the output of this is open loop system, so its output consists of only numerator term. So this is one of the example, and this is somewhat similar to the discrete convolution. As we know that for any system if we are providing input and there is output, and generally system is represented by impulse response h of n. So generally for writing our response, which is output, we use our convolution formula, which is x of n convolve with h of n. So this particular formula, what is the formula for convolution? So here we will discuss this particular formula. X of n equals to summation n equals to k equals to 0 to infinity. We consider for finite, then we can take this is particular value. So here h of k x of n minus k. So here somewhat this particular expression difference equation is similar to the convolution formula. On comparing these two equation, we know that this particular impulse response value is somewhat equivalent to bk. So here we took this particular system impulse function impulse response value, which is nothing but a bk. So here as you can see here, this particular expression, on comparing with our discrete convolution formula, we conclude that h of n is nothing but a b of n. So we took this particular value as the limit is from 0 to m minus 1. So in this way we can have the impulse response in case of discrete convolution if we want to write like that. Okay, now how to realize this particular FIR system? As we know that this particular is only zeros, so for zeros are in the feed forward path. That means their path must be like this. If there is denominator term, that means pole term, always the pole term having the path like this, which is feedback path. So generally for considering numerator term, we use feed forward path, and for considering pole we generally use feedback path. Now how to realize this particular direct form realization? So here we must first realize this. Okay, so as you can see here, in case of, as what is the expression? This is nothing but the expression k equals to 0 to m bk x of n minus k. So here for writing zeros term, for when we open this particular expression, we get this expression y of n equals to b0 x of 0 b1 x of n x of n minus 1, similarly till the length. So how we can draw this particular diagram? Because b is nothing but a coefficient, which is the path followed is feed forward path. So here as you can see, first term is b0 and xn. So this is nothing but the input side and this is nothing but the output side. So first of all we implement this. So this is nothing but a multiplier. So here we use multiplier, and this particular x of n is multiplied by b0, and this is nothing but a adder. So here we use adder because we have another term as well. In order to add that, we can firstly use here adder. So next term is b1 plus x of n minus 1. X of n minus 1 is implemented with the help of delay function. So here we use delay. So after crossing this delay, we can have x of n minus 1, and the coefficient value is, in that case, is b1, and so on depending upon the length. So here as you can see, because FIR system consists of only zeros term, hence the path followed by the coefficient is like this only, feed forward path. Now we can draw this particular diagram in this way also. In discrete convolution form we can draw like this. So here as you can see, we have the expression y of n equals to x of n h of 0 plus x of n minus 1 h of 1, so on. So here first of all we have expression like x of n h of 0, x of n here, and this is nothing but a multiplier component. X of n is multiplied by h of 0, which is added with this adder. Next term is x of n minus 1. So here we use a delay function, and after crossing this delay we can have x of n minus 1 here, and the multiplier term is h of n h of 1. So in this way we can have, this is the two different way of arranging our zeros term in case of FIR system. So in this way we can draw. Now moving on to the next, transposed form of FIR structure. As we know that in transposed form of flow graph, generally what we can do, we reverse the direction of branch and reverse the role of input and output, so that source node becomes sink and sink node becomes source. So here how we can deal with the transposed form of FIR structure. So here this is nothing but a direct form structure of FIR system, in which we can draw like this. So on transposed form, what we can do, we reverse the direction of branch, and this input is shifted toward this and output is shifted toward this. But when we shift the direction तो exact nature of FIR system is not justified. So what we can do, we can tilt our x of n toward this side and this side, so the original arrangement of the figure is maintained. So here, as you can see, after transposing we get this particular expression, this particular realization form. So here, as you can see here, x of n, and this particular, because our limit is start from h of 0 to h of m, so here by reversing the direction, h of m is shifted here and h of 0 is shifted here. So in case of transposed form, in this way we can draw our transposed form of FIR structure. Just reverse the direction of branch, but as you can see, if reverse the role of input and output, so in this manner we are not supposed to justify our FIR structure. So what we can do, we can tilt our figure, and in this way we can draw our transposed form of direct form. This is nothing but a direct form 1 realization, and this is nothing but a direct form 2 realization of IIR system in case of FIR system. Okay. Next, cascade form structure of FIR system. As we know that what we can do in cascade form, if we have transfer function, we factor that transfer function in multiple transfer function in cascade form in product. That means if we have h of z, what we can do, we factor our transfer function like this in multiple transfer function, and individually we can implement this with the help of direct form realization of FIR system, and in cascade form we connect all the transfer function. So here, as you can see, when we factor our transfer function, we can have certain transfer function equation, and in this way we are following direct form realization of FIR system, and in cascade we connect like this. So here, in this way we can draw our cascade form structure of FIR system. Now moving, realization of linear phase FIR system. FIR system has one important property, that is linear phase property. What is linear phase here? If the impulse response is symmetric about the origin, then that particular system has a linear phase. That means because of this linear phase property, there is one advantage is there. That means the number of multiplier we generally used in our system is approximately 1/2, because with the help of this linear phase property, what we can do, we reduce the number of multiplier which are generally used for implementation. So how much multiplier is reduced here? 1/2 of the multiplier is reduced here with the help of linear phase property. So generally linear phase property is characterized by this equation, h of n equals to h of m minus 1 minus of n. So here the length of the sequence must be from 0 to m. So generally we use symmetric property of linear phase. Generally it is used to reduce the multiplier required for the realization. Generally we have some mathematical expression in order to solve for linear phase FIR system. So here, as you can see, we took Z transform of impulse response, which is h of z equals to Z transform of h of n, and on opening this equation we can have summation n equals to 0 to m minus 1 and h of n z ka power minus. This is the standard Z transform formula, and for when our length of the sequence is even and when our length of the sequence is odd. So we have two different formula for that in order to reduce the number of multiplier required for the implementation. So generally linear phase property is generally used to reduce the cost of multiplier which is required in the implementation. So moving, generally our output is nothing but a yz equals to h of z into x of z, and h of z is implemented already. When m is even, so we consider h of z like this. In the previous, h of z is this one, and for odd h of z is this one. So we can be considered only for even. So here we have h of z here, because yz is nothing but a h of z into x of z, and while solving this equation we can have this equation. So for example, m is 4. For example, m is 4. That means the length of the sequence is 4. So on opening this equation, we get this equation h of 0 1 plus m minus 1, that means 3, z का power minus 3, 3 minus 1 4 minus 1, that is by ये x of z plus h of 1 z का power minus 1 plus 4 minus 2, that is 2, z का power minus of 2. So as you can see, the delay function 1 plus z cube having the coefficient value which is common h0, and the delay function z ka power minus 1 and z ka power minus 2 having the common delay common multiplier which is h of 1. So in this way we reduce the number of multiplier. With the help of example we can understand more. When we take the inverse z transform, we can have this expression. Just put m equals to 4 here. So after putting 4, we can have equation like h of 0 x of n minus m minus 1 which is 4 minus 1 which is 3 plus x of n minus 3. So as you know that if we take the z transform plus and h of 1 x of n minus 1 plus x of m minus 4 minus 2, that is 2, x of n minus 2. So as you can see, x of n and x of n minus 3, when we both have the same multiplier function h naught, likewise x of n minus 1 and x of n minus 2 having the same multiplier which is h of 1. Now how we implement this? So we can implement this in this particular structure. First one is direct form structure for FIR linear phase when m is even and when m is odd. For example, we took one example with the help of which we can understand more easily. 1 plus 3 by 2 z ka power minus 1 plus 17 by 8 z ka power minus 2 plus 3 by 2 z ka power minus 3 and plus z ka power minus 4. As you can see, 3 by 2 and 3 by 2 is common here. 3 by 2 and 3 by 2. 3 by 2 and 3 by 2 is common for z ka power minus 1 and z ka power minus 3, and here z ka power minus 4 and 1, this particular two having no coefficient value, so we can take this as a common. So here how we take this particular, so as you can see, h of z equals to, when we took the common, 1 plus z ka power minus 4, 1 plus 3 by 4 common z ka power minus 1 plus z ka power minus 3 plus 17 by 8 z ka power minus 2. So if we have this particular expression, as you can see, 3 by 4 is the multiplier term in which z ka power minus 1 and plus z ka power minus 3 is the delay function which are connected together and having the same multiplier. Likewise, there is no multiplication, 1 plus z ka power minus 1, that means there is the constant value 1. So how we connect? So here z ka power, maximum z ka power is minus 4. So here as you can see how we connect this. If we have z ka power 1, the connection is like this. This is x of n, this is x of, when we are using delay function, here we can have x of n minus 1 and we have x of n minus 2 like this. So when we have this particular, when we have z ka power 4, so how we implement reducing our multiplier? So here we can implement like this. This is also consider, this is consider z ka power minus 1, z ka power minus 1, this one, like this. We consider like this. So how we can implement this one? So this is implemented like this, because this is nothing but a z ka power minus 1 and this is nothing but a z ka power minus 1, this is nothing but a z ka power minus 2, and here because our z ka power is minus 4, so here we can implement like this, and our connection is like this. Okay, and this particular is here, this is nothing for infinite number where the m is even. This is the standard diagram we are considering for z ka power minus 4 only. So how we can implement and how we are using single multiplier for multiple delay function. So here as you can see, our equation is what equation? Our equation is having h of z equals to 1 plus z ka power minus 4 plus 3 by 4 z ka power minus 1 plus z ka power minus 3. This is equation plus 17 by 8 z ka power minus 2. So here what we can do, we connect here the output of this is nothing but a z ka power minus 2, and z ka power minus 2 having coefficient value which is h of 2, यहाँ 17 by 8. Likewise z ka power minus 3 and z ka power minus 1 and 3. Where is 1 and 3? This is nothing but a output of z ka power minus 1, and this is nothing but a output of z ka power minus 3. So minus 3. So both are connected with the help of this adder, and the output is nothing but a multiplied by the multiplier component which is 3 by 4. Likewise, when we want to implement 1 plus z ka power minus 4, so how we can connect there? Here z ka power minus 1, z ka power minus 2, z ka power minus 3 and z ka power minus 4. So we need to connect 1 plus z ka power minus 4. So here this is nothing but a 1. So this is connected here, and z ka power is minus 4 is connected here, and this is nothing but a multiplier component which is the coefficient value 1. So in this way we can draw. So whatever be the transfer function, we can implement like this here, because as we connect two individual delay function with the single multiplier, we reduce our multiplier for the usage of linear phase property of FIR system. With the usage of linear phase property, we generally reduce the multiplier which are generally used for the implementation. Actually, whatever be the multiplier, if it is common from individual part of delay function, so we consider one multiplier with the help of which our implementation cost is reduced with the help of linear phase property. So the connection is like this. If we have z ka power minus 4 is the highest part, that means our connection is like this. That means z ka power minus 1, z ka power minus 2, z ka power minus 3 and z ka power minus 4, if we connect like this. And the output of this two particular is, this is nothing but a multiplier. This particular connection you must understand how this connected. If you want to connect z ka power minus 1 and z ka power minus 3, so here as you can see, this is nothing but a z ka power minus 1, the output, and the output is this is z ka power minus 3. Both are connected with the help of this adder function, and the output is connected with the multiplier function. So in this way we can connect and reduce our multiplier component in linear phase property of FIR system. Thank you.